Okay, hi everybody. I've got
Morning.
more screens today, so I should be able to manage this a bit better. Let me just let everybody in. So I recorded yesterday's, or the whole 3 hours, and I posted it in the, I posted it on the playlist. Now let me see, am I able to hear? Grant, can you say something so I can just see how my sound is with my sys setup?
Test 1, 2.
Okay, so it's coming out of this. Say again, Grant.
Test 1, 2.
Okay, great. Okay, well, it's good to see everybody. Today I have I'm in a different spot because I have 3 screens going on, and I see all of you guys on a giant, not a giant, but a large TV. I'm at a strange angle because it's down here, but should be able to give people more attention, and if people have questions or things like that. So I can see you. You don't have to have your screen on, but if you want to, I can see everybody, and it actually makes it, if I get at least 10 people with screens on, I could teach a little bit better that way. So yesterday I couldn't see anybody, but now I see people. Only 14 people here. Okay, let me let some more people in. I get started every day right on time. So today you can see that lesson, this is officially lesson number 4. And today we're going to learn, we're going to finish up Babylonian math with 2 algorithms that they used. One is for, hold on one second. Hold on. Okay, I'm back. So Babylonians had a square root algorithm that we're going to learn about, and they also had what we now call Pythagorean triples, even though this is thousands of years before Pythagoras. This is going to lead us to 2 algorithms, and on the final exam, if you know the 2 algorithms, you would be able to get those questions right on the final exam. It's funny because I could teach the 2 algorithms probably in about 30 minutes total, and you would have what you need for the final. But this is actually a lengthy lesson because there's a lot that goes into where these algorithms came from and why they work and different interpretations of them. But the interpretations, they will be interesting to you, but I'm not going to be testing you on like, what did this guy think in 1948 the interpretation of this tablet was, and what did this guy think in 1956? It's not. So there are going to be 2 algorithms that are going to be fairly, they're pretty easy algorithms. And in that way, today is sort of low stress, but it is a lengthy day. I am going to work in a break sometime in the middle. So the class is 2 hours and 45 minutes. So about an hour and a half in. So at 11, someone can put into the chat. Oh, that's the other thing. I can see the chat on a separate screen now, so I can see that really well. Okay. If you look at the screen here, you can see that I have a picture of 2. One's a tablet, and one looks more like a rock. But these are the 2 most famous mathematical artifacts from ancient Babylonian times. The one on the left is known as YDC 70. I get the number sometimes. 7289, I think. And the one on the right is the most famous artifact, probably the most first or second most famous mathematical artifact of all. It's called Plimpton 322. And I have actually put into the Google Classroom, I have here, if you look at lesson number 4, among the things there is a document. And this document, as it comes up, which is yours, to have, has drawings of these two tablets. So 7289. So YBC 7289, the round one. A little slow in coming up. Hopefully on your computer, when you bring this up, you're able to see it. I think it's just loading. There it is. So YBC 7289 is this round one with a diamond in the middle. Here's translation of it. It has these cuneiform numbers, which are difficult to read, but here they are translated. So the number on the side is just 30, and then there's two numbers across the sort of diameter of that diamond thing, 124, 51, 10, and underneath it 42, 25, 35. There's also this hand drawing of Plimpton 322. And underneath it, I have a translation of the main two rows, which are called U and D here, basically this row and this row. You're not going to have to read cuneiform. We did that one day just to see, so you could appreciate how much easier it is to use base 10 numerals, but so I'll be translated. Now, we also don't use base 60 very much. We used it that one day, but notice how yesterday, no mention of base 60. Those algorithms, those quadratic formula algorithms, they did not use base 60. We didn't do them in base 60. Of course they did, but we don't need to because the mathematical logic is still the same. Now I have here the Desmos activity, and I'll tell you what the code is. There's actually a link to it over here. Babylonian square root. But the code is, where is it? I go there. Let me dig up the code. Hold on a second. If you click on the link, it's just going to bring you there, but I have a code I want to tell you. Let me just grab it off of this window. Hold on a second. Okay, so the code is 9. I'll put it into the chat. 9RJMBE. Go. Here, I'll send that to all everyone in the meeting. Oops. 9RJMBE. Let me write it down. Also over here, there are some people still coming in. So you can go ahead if you're able to access this. If not, you can send the answers to these questions to me into like a private chat. But if you go to 9RJ MBE in student.desmos.com.
You want us to answer those questions now?
Oh, there's gonna be, let me bring up the first two questions. And this is sort of a warm-up activity. Here, you could continue without signing in. Eventually, I want to give everyone, I want to make a class out of the Desmos so that you'll have like an account. But for now, let's do it this way. Okay, so as a warm-up for today's lesson, there are two questions it's asking you. And the first one is about square root, and one is about Pythagorean triples. Let's get the activity out. Okay, so the first question is, what is the square root of 2 rounded to 4 decimal places? And the second question is, how many Pythagorean triples do you have at the tip of your tongue?
Wait, I have a silly question. Did they know
Yes.
about Pythagoras before Pythagoras?
Oh yeah, yeah. So Pythagorean theorem, Pythagoras is in the year 500 BC. So they knew Pythagorean theorem for right triangles. Babylonians had that, and they also had Pythagorean triples, which Pythagoras didn't do anything with Pythagorean triples themselves. But yes, so things get named often by Western culture, someone in Western culture who gets made, famous for it. But no, the Babylonians had Pythagorean theorem. Everyone had Pythagorean. Every culture had come up with Pythagorean theorem before Pythagoras had. So, as a reminder, Pythagorean triples is something like 3, 4, 5, 3 numbers, so that if you add together the squares of the two smaller ones, it equals the square of the larger one. But would you into the Desmos, or you can just chat it to me, write down what Pythagorean triples you are familiar with, and also how would you get the square root of 2? Or like, how many decimal places do you know of it? Or if you had a calculator, but the calculator didn't have a square root button on it, how would you find the decimal places of square root of 2? So everyone take a few minutes just on your own, not in a group or anything. Okay, so looking over the looking over the answers that people wrote, I see a lot of, 1.4 is of course is how it starts. And then it's 142 would be the next places. Now, those aren't people memorize digits of pi. Most people don't memorize so many digits of square root of 2. 1.41 or 1 point is good enough, approximation for most of our purposes. If you had a basic calculator, maybe you would say, okay, well, square root of 2, I know it's between 1 and 2. So I try like 1.5, but 1.5 squared is 2.25, which is too big. So you say, okay, well, I'll try 1.4, and 1.4 squared is 1.96. Okay, that's too small. So maybe you try, 1.45, and you end up that's, too big. And you just kind of keep going up and down, and you would be able to get decimal places, but that would not be a very, that's a guess and check algorithm. We need something a little better than that. So, and we're going to get that today from the Babylonians. I'm looking at the Pythagorean triples here. I see Antigone says 5, 12, 13, and so does Joel. Beth has that plus 9, 40, 41, and so 5, 12, 13 is a good Pythagorean triple. 9, 40, 41 also is Pythagorean triple. Now Beth mentioned 6, 8, 10. And the question is, does that count as a new Pythagorean triple? Well, yes and no. Yes, 6, 8, 10 is a Pythagorean triple, but because 6, 8, and 10 have a common factor of 2, and it can be reduced to 3, 4, 5, we say 6, 8, 10 is a Pythagorean triple, but it would not count as what's called a primitive. So if I throw in the word primitive Pythagorean triple, 6, 8, 10 comes off the list, because you can take any Pythagorean triple and double all the numbers or triple all the numbers or multiply them all by 4 or 5, and you'll get another Pythagorean triple that will work, but it won't be primitive anymore. So primitive Pythagorean triples, let's see, just looking through the list, any other, looking for more primitives. I see 9, 16, 25. 9, 16, 25, no, that's 3 squared. 9, 16, 25 wouldn't quite work, because 3 squared plus 4 squared is 5 squared, but 9 squared plus 16 squared is not 25 squared. But I do see a 12, 16, 20, which is a 3, 4, 5 times 4, 5, 12, 13. I see an 8, 15, 17 thrown in there. So most math teachers are aware of 4, 3, 4, 5, 5, 12, 13, 8, 15, 17. Those are the 3 that have the smallest values in them. There's one more that pops up. I'm just looking through the list to see if there's any more. Oh, I see a 21, 28. Oh, 21, 28. Okay, so that's multiple. Okay, well, the fourth one that math teachers often use are 7, 24, 25. Those are the big 4. Any other Pythagorean triple primitive, the numbers are larger than 25, the C value. There is one really surprising Pythagorean triple. There's an infinite number of Pythagorean triples, but one of the most underappreciated Pythagorean triples, and if you're a math teacher, you might be shocked that this even is true, because usually in the Pythagorean triple, there's sort of 2 small numbers. Usually in the Pythagorean triple, the biggest number is fairly close to the middle number, like 5, 12, 13, they're just 1 off. 3, 4, 5, they're 1 off. 7, 24, 25, they're 1 off. 8, 15, 17, they're 2 off. Usually there's like a small number and then 2 big numbers, but a underappreciated Pythagorean triple is 20, 21, 29. And if you're a math teacher, you might be excited that you have a obscure Pythagorean triple that has fairly small numbers in it, yet it's not, that's not, like, most people don't know that one, even math teachers. 20, 21, 29. Okay, I think I would like to do the square root algorithm first. So here we have the YBC 7289. YBC 7289, Y stands for Yale. So it's like a 7289. Yale Babylonian collection, piece 7289. About 15 years ago, both of these artifacts, YBC 7289 and Plimpton 322, were on display in New York City. They had a very small museum that had mathematical artifacts. Plimpton 322, which is the most famous mathematical artifact of all, it's owned by Columbia University, and it resides in New York City in storage most of the time, but they took it out and put it out for display right next to YBC 7289, and I was very excited. I went over and saw these two things. They were very small. Plimpton 322 looks like the pictures of it make it look like it's about 2 feet long, like 10 Commandments or something, but in reality, it's only like 3 inches long. And same thing with this YBC 7289. These clay tablets were a commodity back in the day, so you didn't waste them by making giant tablets the size of the 10 Commandments. Okay, so YBC 7289 has these cryptic numbers on them. It has a 30, it has 42, 25, 35, and it has 1, 24, 51, 10. To make this a little easier, they have commas in this thing, but I'm going to put a semicolon here and here, because these are base 60 numbers they're talking about. 30 is the number 30. But 124,
I'm
51,
sorry, I
10.
recall semicolons were used for decimals. So is that not the case?
That's right. Yeah, no, it's a semicolon is the decimal. Well, I usually, when I wrote these, I write it like this: 0, 1, semicolon, 24, 51, 10. When I use them, I don't put commas between the places. They put commas between all the places and did not put a semicolon between the 1 and the 24. So it was like a little ambiguous, like, of course, the actual tablet doesn't have semicolons or commas.
Yeah, how do you know it's a decimal? Because I'm looking at the tablet, it's not clear to me.
Oh yeah, no, you would never know. That's one problem with until they invent the 0 thousands of years later as a placeholder, and the idea of the decimal point, it was really ambiguous. If you said, my grandmother, is 1 year old, well, that could be 1, or it could stand for 60, or it could stand for 3,600. So you have to use the context. Is this person's grandmother really 1 year old? Probably not. Is this person's grandmother really 3,600 years old? Probably not. So that one, so you had to infer, there was ambiguity, and you had to infer it from the context. So now we know from analyzing these tablets that if they had thought of the idea of a semicolon decimal point, they would have put it right here, and they would have put 1 right here, but they didn't. So there was ambiguity in that way.
So, Professor,
Now, if you take this 124, 51, 10, and you change it to a base 10 decimal, it'll be 1 plus 24 over 60 plus 51 over 60 squared plus 10 over 60 to the third power. If you have a calculator nearby, pop that in and let's see what that turns into as a decimal. Everyone take a minute on that. Okay, someone you could do a raise hand in the, now I can see everything. This is great. So if someone does a hand raise, they could tell me what that ended up becoming as a decimal. I should have mentioned, it will be useful to have like a calculator, nearby. Of course, you could use your computer as a calculator. Okay, Beth.
So it's a 1.4142 or root 2.
That's right. It's about 1.142, which is approximately the square root of 2. So on their tablet, this 124/5110 must be the square root of 2. And this diamond is, yes, it's a diamond, but it's also a square, which makes this triangle a 45-45-90 right triangle. And in a 45-45-90 right triangle, the relationship between the two sides and the hypotenuse is s square root 2. So anyone have a suspicion about what 42 semicolon 2535, what that is? Oh, you can do a hand raise. I'm looking over the. Okay, Scott.
30 radical 2.
Say it again.
30 radical 2.
That's right. So that would be the length of the diagonal of this square. Now, remember how I mentioned that that's how most people interpret this thing to be, but actually there's a little bit of another interpretation, because I mentioned there's no semicolons or decimal points. If there was a semicolon there, this wouldn't be 30 anymore. It would be 30/60ths, which would be 1/2. And notice how 42-25-35, if you double 42, so this could also be square root of 2 divided by 2. Could be. If that was the case, the semicolon would be over here. Now, if you double 42-25-35, 42-25-35, easiest way to double it is just to add it to itself. You get 70, but you can't put 70 into base 60, so you just call it a 10 with a carry of the 1. 25 plus 25 is 50, that's 51. And 42 plus 42 is 84, but you can't put 84 into base 60, so you'd have to say 124/5110. And some people speculate that actually this thing was calculated first, because some people are like, well, how'd they get so precise to get the 10 there? Well, it's possible that they figured out square root of 2/2 first, 42-25-35, and then just doubled it to get the 124/5110. 10. No one knows for sure. But how did they get this then? Well, that's what we're going to learn today. Babylonian square root algorithm is coming. Okay, here comes the Babylon. Now, there's a formula, but the formula is not so useful to us because there's an algorithm that's more useful because the formula gets us. We start with an approximation. So let's just get an example. Square root of 5. So here's the big instructive example. Again, today's lesson is really 2 algorithms. Square root algorithm, Pythagorean triple generation algorithm. So everything we've done up until this point, I hope was interesting to you. But as far as the final exam goes and the homework assignment, here comes an algorithm for you. I almost don't want to show you a formula first because the formula only gets you the next best approximation. So let me start by saying this. We know the square root of 5 is between 2 and 3. 2 squared is 4. So we say that our first guess, which I'm going to call x with a little 0 there, is going to be 2, the smaller answer. The truth is you could start with any x0 you want. I sometimes write it like this. I say x0 is, there's a mathematical notation that looks like that. It means the floor function, which just means round down. So it basically means find the integer, the biggest integer that's less than the square root of 5, and that will be our first guess. Yeah, I think I'm just going to show you the algorithm. I don't want to show this formula because it's deceptively, it's not very, it only gets you the next answer, but we want to be able to get more and more accuracy. So here's the way it works. Here's an insight. When you divide something like 9 by its own square root, you end up with its own square root. So if you ever divide something by its square root, you should get as your answer the square root also, because the square root is the thing multiplied by itself gets you that number. So if you divide a number by its own square root, the answer should be its own square root. 81 divided by 9 gets me 9. So that's an important insight. When you divide something by its own square root, so you say, well, that's not such a big deal of an insight. That's just definition of square root. But if you divide 9 by something smaller than its own square root, so this is less than the square root of 9, and the answer will be greater. And if you divide something by something that's greater than the square root of itself, so 4 is greater than square root of 9, and you divide, the answer will end up being less than. So again, if it's equal, if you divide by its square root, you get its square root. But if you divide by something different, well, you're not going to get the square. If the answer became 2, it would mean 2 is the square root of 9, which is not. So those are the only 3 things that can happen. You could either divide, the thing you divide by is either equal to the square root of 9 or less than or greater than. So these are like the 3 things that can happen. So if I take 5 and divide by 2, I get 2.5. Does someone want to, in the comments, make some sort of conclusion right now? Some kind of observation based on that 5/2 is 2.5? Go for a hand. You could raise a hand in the Zoom and I'll call on somebody. What can you say about the square root of 5 at this point? Oh, someone raised their hand. But where are they? They usually pop to the top.
It's me, Professor.
Okay, Scott. Oh, I lost you.
I would say that's the square root is greater than that.
Greater than 2.5?
Yeah.
Okay, let's hear. Why do you think it's greater?
Because we know the square root of 4 is 2, right? And then
Ah,
the square root
well,
of
it's definitely
9
bigger
is
than
3,
2.
right? And then the square root of 9 is 3. So I'm thinking that this is giving you kind of a floor to go above.
I got you. It is 2 point something, but
Yeah.
whether, it might be 2.4, it might be 2.6.
Right.
Anyone else want to make any sort of observation at this point? The fact that 5 divided by 2 is 2.5. Molly?
It should be between 2 and 2.5.
That's right. You see, we don't know. Well, we know 2 is less than the square root of 5. So therefore, when you divide by it, if the thing you're dividing by was less than the square root, then the other thing would be greater than the square root. So we can say the square root of 5 is between 2 and 2.5. Now you might say, well, what if I didn't know? What if I didn't know whether 2 was greater than or less than? So let's say I divided 5 by 3 and I got 2.6. Is that what I would get? No, I get 1 point. I wouldn't get 1.6. I would get 1 and yeah, I get 1 2/3. So 1, let's write it as 1.6. Even if I didn't know whether 3 was bigger or smaller than the square root of 5, it wouldn't matter. I could still say it's between these two numbers. Because if the 3 is bigger than 5, this thing will be less. If 3 is bigger than the square root of 5, 1.6 repeated will be less than. And if 3 was less than, then this number would be bigger. So we could say the square root of 5 is between 3 and 1.6 repeated. Of course, this is a better approximation. Like that's more, between 2 and 2.5 is more accurate than saying it's, I could say it's between 0 and 1,000,000, but it wouldn't be that useful. Okay, so let me come back here or start over. So the goal is to get the square root of 5. Our first guess was 2 because square root of 5 is between 2 and 3, and I'm going to use the number that's bigger than. So I'm going to use the biggest number that's less than the square root of 5. Although this algorithm would work if I chose any number, but I want to choose the thing that's a little less than the square root of 5. So here comes the algorithm now. I just want to make a quick note on this. This is still just part of the note. So we know square root of 5 is between 2 and 2.5. If you had to guess now, what is it? And you have to say something, right? It's not 2, it's not 2.5. If you had to guess something like, okay, we're building this thing right now. We need to use an approximation of square root of 5 right now. What would you say?
2.25.
2.3.
2.25.
Maybe 2.3. Which you could use even more
2.1.
decimal places. Yeah, is it? So we don't know for sure. Is it closer to 2 or to 2.5? So I think there's some ideas. Okay, well 5 is just a little bigger than 4, so maybe it's like closer. And you might be right. It might be closer to 2 than it is to 2.5. But for our purposes right now, we're not going to think that deeply into it. We're just going to take the average. But I think people are thinking even deeper than that, like, maybe it's not right in the middle. Maybe 5's a little closer to 4 than it is to 9. So, Then again, 2.5 is in the middle. It's not like 2.9. For our purposes, our next guess is going to be 2.25, although I'm going to ask that we write it as an improper fraction. 2.5 is 5 over 2. Wait a second. 2.25 isn't 5 over 2. It's 9 over 4. Two and a quarter. Here it comes as a formula or like an algorithm. X1, the new answer, is the old answer, the average of, say, see this, the over 2, it's the average of the old answer, X0, and 5 over the old answer. See, this was the 2, and this was the 2.5, and this 2 is just because we're taking the average. We're going halfway between the two things. Now, I'm going to ask you to go like this. So X0 is equal to 2. X1 is equal to 2 plus 5 over 2 over 2. I do not want decimals. What? No decimals. I want improper fractions. If you want, after the improper fraction, if you want to then turn it into a decimal, you can. So now we have our original approximation and our better approximation. You could check it out. You could do 2.25, I have a calculator here, 2.25 squared. I'm just going to make a note for us in parentheses. 2.25 squared is 5.0625. So 2.25 ends up being pretty good. 2.3 squared is not as good of an approximation. That's 5.29. So 2.25 is really good, but maybe it's 2.24. You know, maybe we could do better than that, and that's what's going to come next. Here it comes. By the way, there is a formula that would get me directly to this answer without doing this averaging, but I don't like that formula because that formula doesn't let me go the next step. Now that I know 9/4 is a good approximation, I can get an even better one. I'm going to write it like this. X2 is the average of X1 and 5 over X1. That's the same idea. I'm taking the average of my current guess, which was 9/4. Now, I don't know if 9/4 is bigger or smaller than the square root, but it doesn't matter. Because when I do 5 over 9/4, if 9/4 was bigger, 5 over 9/4 would be smaller than the square root. If 9/4 was smaller than the square root, 5 over 9/4 would be bigger. Either way, I take the average of those two. So I'm going to write it like this. X2 is equal to 9/4 plus 5. 5, if I was taking the square root of something different, that 5 would be something different.
Times 4 over 9.
Oh, so yes, yes, you can 5/9. Simplifying this, it's actually kind of tricky. Why don't you take a minute to see if you can simplify this expression? Can you simplify it such that there are just a numerator and a denominator? It's deceptively hard to do that. Everyone take a minute to try to simplify 9/4 plus 5/9 over 2. Go ahead. I'll give you a minute to do that. And as you can see, it became 161/72. It is not, even though it's just fractions and adding and all, it's very easy to make a careless error on a question like this. It's very, so look at my steps. I showed all my steps. I guess the only step I didn't show at the end was 161/36 times 1/2. But definitely, what we call our arithmetic skills. This, in one sense, this question here, this simplification is something that you would, maybe assign to, to a grade school student, to test that they know the different adding fractions, common denominators. But on the other hand, it is easy. I often make a careless error on these questions. Oh, and yes, I see that if you put that into a calculator, 161/72, you end up with a decimal approximation of 2.2361111. But even better than that, if on a calculator you were to square 161/72 and square it, I have a calculator here, 161 divided by 72 squared, you end up with 5.00019. So as you can see, that is a really good get. I'm going to write this out as a formula for you now. So to get the square root of m, x0 is, I'm just going to write, I know it's kind of like fancy notation. I'm sorry, this makes it look much harder than it is. That's basically saying the number that's a little bit less than the square root. And then in general, we say, I like to say xn plus 1 is equal to of xn plus m over xn divided by 2. That's the formula as it's a recursive formula.
And they were doing all this in the Babylonian numbers.
Yeah, so they had a pretty good decimal system for their Babel. Oh, but they didn't have very good. Yeah, they'd have to do it all with the Babylonian. Yeah, with it was hard to divide.
Yeah, I'm just looking at, squaring these numbers with Babylonian numbers, all these decimals. Seems like an arduous task.
Yes, yeah, it would be pretty hard. Not most people didn't learn it. They were just a few people that needed to know math in the whole society.
Professor, what is
Now-
what is the value for the U? I don't quite get where the U came from.
Oh, do you mean the N?
Or, oh, that's
These
an
things?
M? Wait, no, on the X, isn't it U? Or is that an N? Oh, it's an N.
That's an N. This is just a fancy way of saying that, and I'm gonna put this in parentheses. If you don't like that, you could say, I'm gonna go like this: x1 is x0 plus m over x0 over 2. Then I'm gonna say x2 is whatever x1 was plus m over x1 divided by 2. X3 is x2 plus whatever m was over x2 over 2, and I'll say dot dot dot. This here is a fancy what's called recursive definition, but you actually don't need the fancy recursive definition. This thing is telling us that if you know x0, if n, it looks like a u, but if n was 0, then n plus 1 will be x1. Next answer is based on x0, and x2 is based on x1, and x3 is based on x2. So no, you do not need this recursive formula. If you understand, if you understand that if you look at this and say, okay, I get it, I just take the last answer and do this with it, and then I take the next answer and put it here and here, and the next answer and put it here and here, and keep going to get better and better approximations.
I appreciate that follow-up with the numbers. Thank you.
Sure. Now, if I wanted to on this question, now that I got the 161 over 72, it would get pretty ugly. But I could say x3 equals 161 over 72 plus 5 over 161 over 72 over 2. And somehow it would be really hard, but I could do it. And I could actually keep doing that to get better and better approximations. And now I have a challenge for you. In groups, would you go ahead and try to do this process to get the square root of 11? So x0 is given to you. I just gave it to you as 3. And go ahead, get x1 and x2. On the final, I would probably have you stop at x2. In other words, like over here, the 161 over 72. I usually, on a final exam, just care about x2, because if you know how to get from x1 to x2, in theory, you could get to x3. Oops, sorry, I moved this. So on the final, I will not ask you to go beyond x2. But on the homework assignments, I will sometimes ask you to go to x3. So I'm going to put you into groups now.
What about
And
X?
let me see.
What about X naught? Would you be asking us to use it?
That's just your that actually could be anything, but I like to choose the biggest integer that's smaller than the square root. So like, because the square root of 11 is between 3 and 4, I'm going to use 3 as my x0. This process would actually work if I picked any number for x0, but your answers would be like a little bit different. They would still be getting closer and closer to the actual answer. But I'm going to ask for us to pick as our first answer the answer that's a little bit less than the square root. So I'm going to put you into groups. And I was thinking, some people said, well, I don't, maybe the math teachers and the math majors should be in different groups. So I think, let's see, I can let you choose your own room. I'm going to make 6 groups. I'll make groups 1, 2, 3, and 4 will be math teachers, and groups 5 and 6 will be 1, 2, 8. There only needs to be 5 groups. So 1, 2, and 3 will be for math teachers, and 4 and 5 will be for math majors. And you could choose whichever group you want to go into. So here we go. Let me see how this works. 5 breakout rooms. Oh, I see. Yeah, so 1, 2, and 3 are for math teachers. 4 and 5 are for math majors. You can assign yourself into them. Let's see how this works. I've never done this before. So let's see how it goes.
What was the breakdown again? Group.
1, 2, and 3 are for the math teachers, and 4 and 5 are for the math majors.
Professor, I don't see an option to choose. Can you just put me in 3, please?
I don't see an option to choose either. If you could just put me in any one of them, 1, 2, or 3.
Okay. Was
Same.
that John just now?
Yeah, that
John,
was-
you want to be? John, I'll put you into 3.
Okay.
Okay. Grant, you want me to put you into a room?
Yep. 1, 2, or 3.
Okay. Okay. And Joan?
Yes, 1, 2, 3, Professor, please.
Okay.
Thank you.
Okay, everybody. Welcome back. Hold on, I have to bring everyone back here. So I have on the screen, and I was able to see, you know, everyone's progress. Where is everyone? Hold on. Where is that? There is everyone. So if you look on my screen, you can see the answers went from 3 to 10/3 to 199/60. And if you are real careful, you're able to get, oh, by the way, I reduced 20/6 to 10/3. If you left it as 20/6, your answers might be like equivalent, but with bigger numbers. But if you got 79201 over 23880, that's great, because that's what the homework has you do. And if you got 199/60, I expect on the final exam, I would only have you go out to X2. So be kind of ready for that. I really want you to be ready for this final, because over the years, I haven't made such a big deal about the final, mentioning it every day. And sometimes people, you know, we have a couple more weeks, and this algorithm is not so hard right now. But if you don't look at it again, you know, until the final exam comes up, you might have forgotten how it works. Now, just to show you, I went to graphing calculator here. So if I take that 199/60 and I square it, you can see it's 11 points, you know, 0.00027. So that's pretty good approximation. But how good is that 79201 over 23880? Well, it can't be exact, because square root of 11 is irrational. However, it's so close that even on Desmos, when I square it, it just says 11. It doesn't even say 11 point something. So that's a good approximation. That's called a rational approximation. Anytime you take an irrational number and somehow create a fraction that's very close to it, it's called a rational approximation. I wonder, Wolfram alpha, that will surely give some decimal places, because it's, you know, so accurate. So Wolfram alpha. So if I go over here.
Sorry, Professor, I have a question. Why do you put on square? What is the meaning?
Well, if it's really the square root of 11, if I square it, I should get 11. So I squared it at the end. I know what you're saying. Maybe I could just compare the 3.316625 to the actual square root.
It's close, yes. You say to proof. Yes, okay. Makes sense.
By squaring it.
I put it in the chat.
Oh, I lost the chat. Hold on a second.
Okay.
Here it is. Okay, so 11 point, a bunch of zeros and a 1 and a 1.6. Actually, Wolfram alpha is saying 1.75, but well, we can all agree that that is really, really close.
Yeah. Professor,
So,
I made an observation during the calculation, and I don't know if it's random or if it's any value to it, but I noticed the two numerator fractions, the numerators with one value apart with the same denominator. Is that it all, is it random, or is there some meaning to that? In other words, it's 39,601.
yes. Very interesting. So this is really interesting. They're so close, those numerators.
Right.
It can't be just a coincidence, because it wouldn't happen twice like this.
Right.
But I don't know. I don't know why that happened. Now 199 times 199 versus 660 times 60. I'm not sure. That's a great observation, though. I have to think about how to prove that.
Yeah.
Good observation. I love those sorts of observations. I don't know. I'm knowing me, I'm going to fiddle around with that after class today.
Cool. I can't wait to see what you come up with.
Yes. Now, I just want to mention now to cycle back before the break. If you did this process with the square root of 2, I'm just going to jump to what would happen. X0 would be 1. X1 would become 3/2. X2 would become 17 over 12. And X3 would become, hold on, I want to say this number right. 577 over 408. Various cultures throughout history have come up with 577 over 408 as a really good approximation of the square root of 2. Unlike the square root of 11 thing we had with numbers were like in the thousands, these are fairly small numbers, 577 and 408. If I come over here onto Desmos calculator and do 577, whoops, 577 over 408, and I square it, you can see it's very, very close to 2. 577 over 408 as a decimal is 1.41421568, 627. And now to cycle back to YBC, Yale Babylonian collection. Remember, it was 01 24 51 10. There's speculation that that was their approximation for 577 over 408, or at least a close approximation to that. No one really knows for sure, because I found that if I change this 10 to an 11, it's actually a little bit. Oh, I'm sorry. I'm not showing the whiteboard. So as I was saying, if you do this process for this, but do for the square root of 2, you'd eventually get 577 over 408. The decimal approximation for 577 over 408 is very close to the decimal approximation of the Yale thing, this 1245110. Except I looked into it and found that if I change this to an 11, it's even closer. But if I change it to a 10, it's actually closer to the actual square root of 10 of 2, I mean. So it's a bit of a mystery exactly how the Babylonians came up with this approximation for the square root of 2. We do know, though, that if you look up what's called the Babylonian, the thing I just taught you is called the recursive Babylonian square root method, even though it doesn't agree, it doesn't get you this thing if you tried it, so it's sort of mysterious. Anyway, but it is known as the Babylonian square root method. Okay, I think I want to now give us the 10-minute break. So 10:49, I'll give you an 11-minute break. I'll see everyone back here at 11 o'clock.
Thank you.
Okay, you too.
Okay, everybody. We're back from the break. I mentioned just before the break that this algorithm I just showed you does not give us this exact approximation of the square root of 2 if we did it, but you should know that there are other square root questions in Babylonian tablets where the method that I just showed you does agree with the answer that they got.
Professor,
So
did you
that's-
restart the
that's-
recording? Did you restart the recording?
Yes, I restarted. So there are other instances. Hold on, let me close the door. Close the window. There's some people doing yard work outside. So there are times in Babylonian tablets where they have square root approximations that do agree with what this process would get you, and that's why they've kind of speculated that this is what their algorithm was for getting the square root, and it is called the I just realized my computer's going to run out of juice in a second. Hold on a second. Okay, hold on.
Did we just lose him?
think his battery ran out.
Oh, okay.
Okay, everyone. Sorry about that snafu. I forgot that when I first of all, can people hear me? Hey, everyone. Sorry about that. I forgot that when I do my big setup with all my screens, my laptop needs to be plugged in. Otherwise, it goes. Can people hear me?
Yeah.
Yes.
I can hear you.
Okay, good. Okay, so I'm going to have to be over here now until this computer charges a bit. That's okay. Give me a second to get my my iPad. So hold.
John, you're on mute.
Okay, everyone, I'm almost back in business, and sorry about that snafu. Let me. This. Okay, just be another minute. So the break lasted a little longer. I'll remember for the future too. My system when I'm doing all my screens is very complicated. So there's a lot of wires all over the place, and I left that one off and I have to reset that up. But that's okay. I'll be back in a second. Have this up and running. I just have to get. Okay, we're there. And we're here. And we're there. Okay. Well, I don't have all my screens anymore because I have to be by the plug, but that's all right. So now we have the second part of today. Basically, you know, there's only 16 lectures. So that would have been great for a single class period, but we have these sort of double length periods. And the second part is about Pythagorean triples. And those are related to the famous rhymed papyrus. So I'll just right here. Not rhymed papyrus at all. That's also an important thing, but that's in Egypt. Talking about Plimpton 322. So they found all these tablets in what's now Iraq, Babylonian, Babylon. I don't know if they call and there were shopping lists and various things. But this one is the most famous mathematical artifact because they were shocked when they analyzed it. And you looked at this once before and kind of looked at the text. And it's hard to, you know, to read it. So what I did over here is I put into page 3 a translation of, and by the way, can we see this whole screen? Because there's, when it's the iPad, can we see that? Yes, this looks good. So go over to page 3. And if not in the document here, I have a translation also, but I'm most interested in these two rows. Oh, here it is. These rows, 119, 169. First of all, if I come over here, it's not easy to see the these numbers. Like this one over here, there's a big 1 here, which is basically 01, and this confuses a lot of people because they make 1 usually looks like that, but sometimes they make a really long, skinny one to represent 60, and here was 59, so that was 119. Whereas this one over here was 02, and this is 49, which is 120. 2 is 260s is 120 plus 49 is 120. So it was 0149, which was 119, and 0249, which was 120. And that's why if you come over here, you can see row 1, sorry, not 120, 169. 120 plus 49. So you can see over here in this column row 1 has 119 and 169. And when you do it for all the numbers, Plimpton 322 has 15 rows. And these are the numbers in the important columns in those 15 rows. 119, 169, 3367, 4825. And it's bizarre. There are large numbers. There are small numbers. They're not in any, they seem to be in like a random order. But what they realized, and maybe they realized it by seeing 45 and 75. 45 and 75. 45, they knew that there's a 3, 4, 5 right triangle. And 45 is 3 times 15. And 75 is 5 times 15. And it turns out that if you take any of the numbers in this row, for instance, in the first row, let me get this going. 119, 169. If you do 169 squared minus 119 squared, a calculator, you get, in this case, you get 14400 square root of 169 squared minus 119 squared does end up becoming 120. So what they realized is that every single one of these two numbers were the B was the, I really should call that column C instead of B. I made a mistake there. So I should be calling that I should be calling the middle column C. But I didn't. Those three numbers form a Pythagorean triple. And since I wasted some time there, I'm going to go to the next page to show you all the numbers filled in. Okay, so Plimpton 322 is a list of 15 so-called Pythagorean triples. They don't have the third number, but it's too much of a coincidence.
Are they primitive triples or? Oh.
No, they're not primitive, because you can see the 45, 75, 60 is kind of like a 3, 4, 5 times 15. So you can go over to this page, and this raises a lot of questions. They found this tablet and they said, wow, that's pretty amazing. Then they had to start interpreting. In the chat, what are some questions? If you found this tablet and you figured out that it was Pythagorean triples, what are some questions you might wonder about it? Type into the chat any questions it would like raise for you if you found this tablet. You'll see some questions in the chat.
I'm sorry. So were the C and C over A columns actually on the tablet, or
No,
we're adding that?
good. I added that in. Yeah, the C and the C over A are added in. Okay, type in some more questions. These are great questions. I see. Why would they do this? Why is C over A going up by a little? What would this be helpful for? Okay, more questions. Maybe helpful for building things. Great. Would this be helpful for building things? Okay, any other? How did they get the numbers? Why aren't the numbers in order? Okay, these are all excellent questions. Yeah, was the order important? How did they get them? Is this dealing with geometry in some way? Okay, great. These are excellent questions. First thing I can answer, no one asked specifically this about how there's large numbers, what seem to be large numbers and small numbers. If you're wondering why the numbers are getting big, then small, then big, then small, that's probably because we're thinking of it as 119, 169. But if you throw a decimal point before all of these, they would just be numbers between 0 and 1. So they wouldn't really be much bigger, just like 0.15 is not bigger than 0.2, even though, or 0.15367 is not bigger than 0.2. So if you stick a decimal point before these, or base 60, or just any decimal point, regular decimal point, suddenly they would still jump around a bit, but it wouldn't seem to be getting like large numbers and small numbers. Now, let me get my notes, hold on a second. Okay, so in 1945, a mathematician, historian, had a theory, and that's where the C over A comes in. He noticed, his name is Neuenberger, he noticed that—
Professor,
yes,
is that column C over A correct though? Because you said C was supposed to be B.
yeah, I should have called it B over A.
Okay.
Just because C is like the hypotenuse. So, so Neuenberger noticed that if you divide what I'm calling, if you divide the C, which wasn't given, by the A, these numbers go up. See, C and A are very close to each other for number one. And as it goes further and further, C and A get less close to each other. So they seem to be forming some kind of a progression, but not really. It's going up by 0.02, and then it starts going up by 0.06 and 0.02 and 0.05. So if I come over here, I actually gave you a link to this. I have a Google sheet here. Okay, so if I come over here and I drag this down, it will figure out, it will calculate the hypotenuse for all 15.
So Professor, is C over A just establishing a relationship between the legs of the triangle?
It is, yes. So the legs of the triangle are important. If this is like a geometric interpretation,
I'm still confused with the mislabeling of the columns. You're saying you're calculating the hypotenuse, but what you're really calculating is B.
yeah, that's right. I calculated out the other leg. So here I'm going to draw a triangle with the 119, the 120, and the 169.
All right. So what is the point of C over A then if you're just calculating the two legs and not the hypotenuse?
Well, the C over A, not the C over the leg over the leg, the big leg over the small leg. As if I go to the very last one on the chart, it's 45. It's 45 and 28. So you can see what happens is that when this is 45 and 28, what happens is that this ratio is bigger now, which causes this angle to be bigger than that angle. See, in the beginning, for the first one, the angle's practically 45 degrees. I'm going to write near 45 degrees because it's almost a 45, 45, 90 triangle because 119 and 120 are so close to each other. But as that ratio gets larger from about 1 to about 1.6, if you were to draw these triangles, you would end up with a bigger angle. So there was speculation that maybe these were like instructions for building, for building things. If I want to create a certain angle, I have these ratios, these side lengths that would cause that. I mean, it's not clear. No one knows that that's why, because it really you wouldn't need something this sophisticated to do that. But that was an early theory. So this Neuenberger guy calculated out all these ratios. And then he took the inverse tangent of each of them to figure out what's the angle. And he noticed that the angle was going up by about, half a degree each time. Not exactly. So I have here on this, I made another column that says like how much did the angle go up by? And it's not consistent, but it goes up by about half a degree, half a degree, half a degree, a little more than a degree, half a degree, degree. So Neuenbarger said that the Babylonians invented trigonometry, that that this shows that they kind of had like a way almost of like doing trigonometry. Now that has been kind of debunked. This was a very ambitious reading of this tablet. So that was in 1945.
Do you think this was kind of like a engineering rule book if you're going to build a room or a structure, like maybe like they would give it to people who built buildings?
It could be used for that, but there'd be easier ways to do such a thing. So yes, they did speculate that it would be somewhat useful, but there'd be other things just as useful that would be much simpler than doing all this. So I will tell you what the modern interpretation is in a few seconds. Another question that people wrote down was, how did they come up with these numbers? Like, what was their algorithm? And that's the main thing I'm teaching you today. But I'm also going to give you more interpretations. So in 1957, they came, because Neuenbarger, who had this trigonometry theory, he had also a theory about how they got these numbers, but it didn't make any sense. Like there were too many holes in his reasoning. And that's where in 1957, I think his name was Braun, he figured out the algorithm that they used to come up with these Pythagorean triples. And I'm going to show you that algorithm, and then I'll tell you a little bit more about what this chart, what they now believe Plimpton 322 is. And it's got a surprising answer to it. So here comes the math now. Now I mentioned today was going to be two formulas, an algorithm for calculating square roots, which we've done, and now an algorithm for producing Pythagorean triples. Check this out. If you remember yesterday, I mentioned the thing that the Babylonians really knew really well was that a plus b squared minus 4ab
A minus b squared, yes.
That was like their great achievement, to notice that relationship. And then they did stuff with it, including creating Pythagorean triples. Do you see how this formula, it resembles a Pythagorean triple? This is a perfect square. This is a perfect square. This thing isn't. But, it's like, at least we kind of see the genesis of a Pythagorean triple, kind of like c squared minus, b squared. I'm sorry, I shouldn't be using a and b if I'm going to do that. So I'm going to say z squared minus, y squared equals x squared, something like that. It has the feeling. So that's just an observation. But in particular, check out this thing. If instead of a and b, I make b the reciprocal of a. Take a minute. What would happen if you simplified that? You could do, there's a sneaky shortcut, or you could just work it out. So everyone take a minute to work out what this simplifies to.
Equal by 4.
Equals what?
4.
4. Yes, just the number 4. If you don't believe it, you could do FOIL and watch what would happen. Sorry, dead spot on the iPad. x squared. When you do FOIL, x times 1 over x is 1. So you end up with plus 2. Or if you want to be extra sneaky, you could say that it's kind of like a is x and b is 1 over x. So the difference is 4ab, which is 4 times x times 1 over x, which is just 4.
Can you go back to the previous slide for a second?
This one?
Yeah. So they only had two of the numbers, the hypotenuse and the one of the legs. Could this be why it resembles the Pythagorean thing, but it's not quite?
Well, it resembles, right, because we have two squareds, something minus something, something squared minus something is something squared. So
right. And they had two squares, basically.
Yes, that's right. If they're trying to make a Pythagorean triple, it's hard because, most squares don't become a Pythagorean triple. So it's tricky that way. We're going to try to force that to happen with this relationship. Now, if I divide everything by 4, I end up with a different identity that's going to be useful to us. And here it is. X plus 1 over x over 2 squared minus x minus 1 over x over 2 squared. That just equals 1. I divided everything by 4. And I'm even going to now throw that 1. I could have done this with the 4, but I didn't. 1 is a perfect square. So is 4. There's probably a simpler algorithm. It's not the one that they used where we don't divide by 2 and we use the 4, but I'm going to do the more scholarly thing. So this is a fact. If you plug any number in for x, this will work. Let's try x equals 2, just to see what happens. 2 plus 1 over 2 squared minus 2 minus 1 over 2 squared. I'm just going to write equals just to see, does it become 1? This becomes 5 over 4. That's 5 over 2. And this becomes 3 over 4. So it does equal 1. No, it doesn't. Doesn't equal 1 at all. Wait, 5 over 4 minus 3 over 4. I got myself so confused. What happened there? Hold on. 2 minus 1/2 is 4 has 3 is 3/4. So weird. 5/4
Did you
minus.
get to square them both?
Thank you. 25 over 16 minus 9 over 16 equals 16 over 16, which does equal 1. Thank you. So this identity is key. Because look at these numbers. When I put x equals 2 in, this thing here becomes 5 over 4. And this thing here, different color, becomes 3 over 4.
Well, those are the numbers in that first Pythagorean triple, right? The 5 and 3 and the 4.
That's right. And that's our Pythagorean triple, 3, 4, 5, because I'm going to write this 1 as 1 squared, which I'm then going to write as 4 over 4 squared. So the Pythagorean triple is, so I'm just going to make a note here, 5/4 squared plus 3/4 squared equals 4/4 squared.
No, minus, right? Minus.
Minus, thank you. Now, those are all fractions, but that's okay. So 5/4, 3/4, 4/4 is a Pythagorean triple, but you're not really allowed to use fractions in Pythagorean triple. Is a Pythagorean triple. I'll put quotes around it. But if you multiply everything by 4, you get 5/3/4. Now, good news for you. I'm going to turn this into just a really quick algorithm that will take only 30 seconds to generate a Pythagorean triple. So here we go. New page. Formula. X equals anything you want. I'm going to say any fraction. Greater than 1. The A value, the C value is going to be x plus 1 over x over 2. And the A value is going to be x minus 1 over x over 2. And the B value is going to be 1. That's it. Let's just watch it in action, though. So this is the thing that I wanted to show you today, the second thing. I have more to say about the tablet and questions to answer about it. But if you write this down, this is the formula. Let's watch it in action. Let's say x equals.
Hey, Professor, I have a question, though. Going
Yeah.
to that table, they kept going away from 1, though, didn't they? Like it started at 1, then it kept getting bigger than 1? When
The ratio,
Yeah.
ratio between A and B, or whichever one was bigger. I guess the ratio between A and B was changing.
Right. Okay.
So the way the A changed. We're going to get into the order and everything in a minute.
Okay.
But for now, let's just see what happens if I pick 5/2. Just I could pick any fraction, any improper fraction or integer that I want. According to this formula, C is 5/2 plus, instead of doing 1 over 5/2, I'm just going to say 2/5 over 2, which turns into 25 plus, the common denominator is 10. So 25 plus 4 over 10 over 2, which becomes 29 over 20. That 29 and 20 are actually two of the numbers in the Pythagorean, in the triple, but let's just also do the A. A is 5/2 minus 2/5 over 2, which turns into 21 over 20. At this point, I permit you to just take the three numbers you see and say that's the answer. 20, 21, 29 is the Pythagorean triple. But if you want to be more rigorous and you want to say C equals 29 over 20, A is 21 over 20, and B is 20 over 20, and then multiply everything by 20, you can do that. So this is the algorithm. And now I'm going to give you a chance to go to work in groups and do this algorithm twice. Once with x equals 3/2, and once with x equals 12 over 5. And on the final, that's a very potential question. Use x equals 12/5 to generate a Pythagorean triple with the Plimpton 322 method. So I'm going to send you into groups now for, I'm going to send you in for about 15 minutes because, like I said, today, my goal was that you know how to do the square roots and that you know how to use this algorithm. after 15 minutes, we'll go over these. And then I have some stuff to say, some mysteries of Plimpton 322 to go over. But as far as like the homework, knowing this formula will serve you very well. Now let's see. I hope I didn't lose the breakout rooms. I probably did. Oh, I didn't. Wait. I think just to say in room 5, were there just 2 people in room 5? I'm gonna recreate and have you pick your rooms again. 1, 2, 3, 4, 5 rooms. Let participants. So rooms 1, 2, and 3 for math teachers. Room 4 and 4 for math majors. Do these 2 questions. Talk about them. Type your answers into the box. And if you're math majors and you want to like discuss this in more detail, you can. But let's go for 15 minutes, nice and leisurely. See if you can get both answers. Okay, into the groups now.
Professor, can you put me back into room 3, please?
Yes.
And same, put me in a room.
Okay, so 1 sec. All these names are popping around so fast. So Scott is going into room 3. Who was that? Grant? Which room?
Yeah, whichever one. It doesn't matter.
Okay, I'll put you in room 2. Joan, what room do you want to be in?
1, 2, 3, Professor.
Okay.
Thanks.
And Arafat?
Room 4, please.
Room 4?
Yes.
Okay, everybody, we are coming to a conclusion.
Professor, would you want us to plug in the a squared, the c squared, and the b squared fractions and do that formula? The
No.
c squared minus a squared equals the b squared?
No, you won't need to.
Right.
So I mean, there, this formula is based on, it's based on this identity that x plus 1 over x over 2 squared minus x minus 1 over x over 2 squared equals 1. But you actually don't have to use that thing. You just have to know this is basically C, whereas this is, I call it A. So if you know that this is how you pick any x you want, and this is how, so you actually don't need these squares. They explain why the process works, so they're important, in that way. But as far as like the final exam goes, and the homework tonight, I'll say generate a Pythagorean triple using the Plimpton 322 method I described and an x value of 3/2.
Oh, I did a lot of extra work then.
But that's okay, because seeing, and I'm like this in math a lot of times. I like to see the connection to what I'm doing, to like the logic of why it works at the same time.
Yep.
So when it just becomes a formula, x plus 1 over x over 2, if that's all you have, you might somehow forget that or do something wrong with it. So it is good to have it. But as far as homework goes, this amount of work would be sufficient. So the first one made a 5, 12, 13. And the second one is interesting because when you do 12/5, I didn't just pick that one randomly. 12/5 turned out to be 119, 120, 169, which is row 1 of Plimpton 322. And I'm going to finish up today with some mysteries. I'm not going to say they're solved, because in history of math and archaeology in general, you can't really solve it except to say the best theories right now suggest this, and maybe some evidence comes out. So how did they pick good x values? Why was 12 over 5 a good x value? Well, look at what happens. What if instead of using fractions, I used decimals? And I took, remember the 20, 21, 29 one that I did? Let's just imagine I did that. I wanted to do decimals because I had a calculator. And I did 5 over 2, which is 2.5. And 1 over x is 2 over 5, which is 0.4. And I plug that in. I would get 1.45, 1.05. And the Babylonians, they didn't have fractions. They had base 60 decimals. So if they did 5 over 2 as their x value, they could have written into the chart 145, 105, 100. That would explain why they didn't reduce their Pythagorean triples. The algorithm led them to 1.45, 1.051, and they don't have to multiply by 100 because they don't write the decimal points anyway. So if you saw like 145, 105, 100, yes, that can be reduced, but it wouldn't have been what came out of their chart.
Wow.
Now, I got more. There's more coming. That's pretty crazy. 5/2 is a good thing to choose. However, 3/2 is not. Because if you're using decimals, 3/2, the reciprocal, 3/2 is a terminating decimal, but 2/3 is not a terminating decimal. In a base 10 world, 3/2 would not be very good. But guess what? In base 60, 3/2 is a terminating decimal. It's 0130 because 30/60th is 1/2. And 2/3 is also a terminating decimal. In base 60, you get more terminating decimals for more numbers than you do in base 10.
Wow.
So in base 60, this would work. 3 halves would be a perfectly good one to use, and you would get 01, 05, 25, 60. So they would have chosen, see, in base 10, you may not have thought about this before, but in base 10, the only way to get a terminating decimal terminates if the numerator and denominator only have powers of 2s and 5s in them. Like, 2 over 25 is 0.04. But if you have anything, any prime factor besides 2 or 5 in a base 10 fraction, sorry, I should say that it's the denominator. The denominator. The numerator could be anything, but only base 10 fractions with denominators that are multiples of powers of 2s and 5s terminate. So 1/10 terminates, or 2/10. It doesn't matter what the numerator is. And 2 over 25 becomes 0.04. Or 3/8 becomes 0.375. So the denominator has to have only 5s and 2s in it. If you throw any other factor, prime factor, into the denominator, even 1/3 is 0.333. But in base 60, the numerator can be anything, but the denominator can have 3 in, can have a factor of 3. That was good. So you get,
And also have 4.
you know what? We do need the numerator also. Oh no, we don't need 4 because 2 takes care of the 4s. But we do need the numerator. Oh, sorry, I'm going to write terminates. But if you want the reciprocal to also terminate for both x and 1 over x to terminate, for base 10, you'd have to have the numerator and the denominator, both be powers, a product of powers of 2 and 5. That's why 5 over 2 worked. But for base 60, the numerator and denominator could have a factor of 3 in there also. And that's why 5 over 12, 12 over 5, sorry, was okay, because that 12 was all right. So it gave them, so they got a lot more options. And that's a mystery of how they would have picked their x's. They only picked x's where the numerator and denominator were terminating decimals in their base 60. Now the order, it does seem that the order was maybe made so that the angle, the ratio got bigger. That can't just be a coincidence. Whether they were using it for geometry, trigonometry, whatever, we don't really know. But it does appear that maybe after the fact, they arranged them in an order so that the ratio between the bigger leg and the smaller leg was increasing. We don't know that that was used for any practical purposes. Okay, but there's a final mystery. Why did they make this chart? What was the purpose of it? And why, in Plimpton 322, the actual one, were there several errors? There were mistakes in it.
Were there teaching errors, or like to show each other scholars, say, hey, like this is what not to do, and this is what to do?
Well, the current belief is that Plimpton 322 was no more than a worksheet accomplished by a student. that the teacher would have given them these numbers, and they would have done an algorithm to find the other pieces. And and the student did their homework, and got a couple of things wrong on it. And then thousands of years later, we found that homework assignment, and based on it, reconstructed, what they did. So the current belief is that it was just a drill. It was a page of practice problems that worked out nicely, the way teachers make, questions work out nicely. That's the current belief. So I have in the if for the math majors, but the math teachers might be interested in this also. Supplemental Math Majors Class 4, I have a video of these two professors discussing it. I also have two documents. One is a pretty easy one from Mathematics Teacher Magazine, where they explain the algorithms, and then Intensity. This article, which I've never even fully digested this article because it's 17 pages long, and it's and they go through all the different theories over the years of Plimpton 322 and the different algorithms that it suggests, and they have pieces of other tablets that they compare to it, and all the different theories, whether trigonometry is related to it. They even have YBC in there, some other YBC. So here's the reciprocal pairs. That's the thing I was just telling you about, how reciprocal pairs are involved. And there's an even more recent article. This article was 2003. These guys in this video talk about how people are still discussing Plimpton 322, and they talk about a paper written in 2011 analyzing it even more.
I'm kind of horrified that somebody could find your homework and then try to extrapolate an entire society's math capabilities on it.
Yes, it makes us, well, our homeworks are going to all disappear. The magnetic, we don't have tablets. So once the internet gets wiped out, all our homeworks will get wiped out also, and the tablets will still survive maybe. I did find recently Plimpton 322 first trigonometry. People are still, like, here's an article. This ancient Babylonian tablet may contain the first evidence of trigonometry. This is in 2017. The trigonometry thing has been debunked. That was first addressed in 1948 when they had that theory. And by 1945, the trigonometry theory was laid out there. And in 1957, they said, no, reciprocal pairs. And then they advanced this even more. But here in 2017, somebody must have, and here's a picture. Oh, wow, here's a guy. This is one of the guys from the video holding Plimpton 322. That's how big it is. I was very surprised that that's how big it was, since I thought it was the size of the 10 Commandments. So
looks like an index card.
Yeah, it was very small. So here in 2017, someone writes an article about how it's in Colombia. Well, now Mansfield. Well, here's the guy talking about, maybe Mansfield is still saying it's not a new interpretation. I should read this. If new interpretation, it would not. You see, this is kind of a weird article because they're saying it's the new interpretation. Maybe there's something even more going on here, but Mansfield definitely knows that in 1948, Neuenberger did the trigonometry explanation. So I was surprised to see this in 2017, except Mansfield is a really big scholar on this stuff. So maybe he found something even newer about it, because he's one of the people in the video, and the video is really good. Okay. Well, it's 12:05. We get a second 10-minute break right now, and we could leave. Homework is only on Delta Math. Now, some people haven't submitted Delta Math homeworks yet, maybe because they were in the math majors and I hadn't explained it very well. So I have here the Delta Math code. You go deltamath.com, do the code, register. I left the old homeworks, assignments 1, 2, and 3. You could still submit those. So I'm going to stick around now. Maybe if anyone has any questions, but I hope you like that. That was pretty heavy, but it really ended with just 2 formulas at the end. If you know how to do, you're in good shape, and a lot of mysteries and theories and
Fascinating history too.
Yeah, that was a hell of a plot twist. It's basically a 7th grader's Lisa Frank notebook.
that's what they're saying, because there were a lot of mistakes.
Yeah.
Okay, so I'll stick
Crazy.
around if anyone has questions. I'll put the iPad back up.
Yeah, I have some questions.
Yes.
Thank you, Professor. Have a good one. See you tomorrow.
Okay, see you tomorrow.
See you tomorrow.
Bye-bye.
Okay, so someone had a question?
Yeah, about the homework, the paper homework, the online Google Classroom version,
The one from the homework 3, or which one?
homework 3.
Okay, yes. I'm gonna post the answers tomorrow because I made it due, tomorrow, but I'll answer any question about it.
I got about halfway through the second part. I
Okay.
got stuck on number 3 in section 2.
Did you skip to the third part? Was probably easier than the second part, just because the second part had fractions, which were annoying, but the third
Yeah.
part didn't. But I'll go over one of those. So tell me one of those, and we'll see what happens.
I think I keep getting confused on when to switch the X and the Y and when to subtract and when to add.
Well, tell me which question. Give me a question number, or you give me the question itself, and I'll talk about it, including how I make.
Section 2, number 3, x squared plus 4x equals 25 over 36.
Okay, so the process is
I got, yeah, I factored it out. Yeah, I got that far. And then the system of equations xy equals 25 over 36, y minus x equals 4.
that's right. It's y minus x, not x minus y, because the y is bigger than the x.
The y is bigger than the
X plus-
x. How do you know the y is bigger? That's what somebody else was explaining to me. Why? How do you know the y is bigger than the x?
It's x plus 4,
Right.
so it's 4 bigger than x.
Oh, okay.
So if you did x minus y, you get negative 4.
Yes. Okay.
So
Yeah,
if
that's
there's
what
a-
I was thinking.
So
All right.
what's funny is that whether there's a plus here or a minus, so imagine I made another question. Imagine the question versus x squared minus 4x.
Mhm.
So that would start the same way. And you still have xy equals 25 over 36. But
Yeah.
what would the other equation be now?
Would it be x minus y equals 4?
That's right. So that's the difference. They both end up with a minus here.
Uh-huh.
But in the second one, the y is smaller than the x. So if you do x minus y. And in the first one, the y was bigger than the x. So you had to do y minus x.
So you always get subtraction then.
For this type of question, always get subtraction.
Okay. So there, all right. So when you start following the steps, you divide by 2.
Oh yeah. So now the steps,
Then,
4 divided by 2 is 2.
so I had that part right.
2 squared
Okay.
is 4. But now you do 4 plus 25 over 36. Because anytime there's a minus here, you're going to do a plus here.
But you're dividing by 2 first.
You do 4 divided by 2 is 2, but then you squared it. It became 4 again.
Oh, I didn't use 4. That's where I got stuck.
Yeah,
So
36
Professor, because these are all subtracted, it'll always be added at this stage, right?
Always. That's right. Any question that's like this, including having a number in front of here, will always end up with a plus at this spot and a minus at this spot, always. The only way to get the other type is to create a question that's like, a plus b, x plus y equals xy equals. And that's the only way to make it happen. Any quadratic equation will end up with a plus in this spot here.
Got it.
Now this one's kind of annoying because it's got the fractions in it. The reason I picked part 2 were all actual questions from a Babylonian tablet, whereas the other ones were just questions I made up because they worked out nicely.
So on the final, will we get whole numbers and not fractions?
Yeah. Now 4 plus 25 over 36 becomes 4 times 36 is 144. So it becomes 169 over 36, which is good because that actually is a perfect square still. And then you can add that to the 2. So it does still work, although the answer ends up with fractions. See, I forgot to show you. I meant to give you a copy of the tablet and show you that those questions were on the tablet, so you'd see like, why am I suddenly doing fractions? So part 2 was like pretty annoying. I kind of regret putting those on there. But
Okay, so then. Okay,
so now you have to do 13 over 6
plus
plus 2,
2,
which is
no, plus 4. Wait, no, we did that right.
plus 2.
Confused.
Plus 2, because you have to add it to the 4 over 2.
Are you writing something? Because I can't see the bottom.
Oh, I'm writing up here. So after I get the 13 over 6, I do 13 over 6 plus 2 is 25 over 6. And 13 over 6 minus 2 is 1 over 6.
We missed a step. I thought it was 6 steps. 1, 2,
1, 2,
1, 2.
4.
Oh, I didn't write it, but yeah, we did it.
So my answer is 25 over 6 and 1 6, but only one of them is X, the other one's Y. Which one is the answer?
The first one, 25 over 6, because you only need the X.
Professor, you got negative 1 over 6?
No, positive. 13
Oh.
over 6 minus 2 is 13 over 6 minus 12 over
They
6.
didn't have negatives.
But in theory, it could have popped up in this question. Now the reason
Oh, because you're doing 2 minus 13 over 6 or 13 over 6 minus 2?
13 over 6 minus 2.
Okay, all right.
And the answer is actually not 25 over 6. It's 1 6. The reason why is X is, one of these is X. The other one is X plus 4. The bigger one is X plus 4, which was the Y value.
Oh.
So it's actually 1 over 6
Or
is
it's
the answer.
1 6.
1 over 6.
That's one last decision to make. The decision is my answer the 25 over 6 or the 1 6? And for that, you go back to here. One of those answers is X. The other one is X plus 4. Well,
So
25 over 6 is bigger than 1 6. So the 25 over 6 is actually X plus 4. And the 1 6 is the X.
oh, so it's 1 over 6.
Oh my,
Yeah, there's a lot of like decisions to make, you know, but like there's 3 big decisions to make. Should it be X minus Y or Y minus X? Should this be a plus, which the answer is going to be yes for that. And then finally, should I pick, which of these 2 things should I pick?
Oh, so that's how all those 4 questions are going to be like.
Yeah.
Nice.
And the Delta math has questions like this, but they'll work out more nicely.
Okay, so we should circle the ones that we think is the answer.
Mhm.
Okay, I'm going to circle now.
Okay, so I hope that, in my sense, yesterday's lesson was probably hard. Today's was actually a little easier than yesterday's lesson. Yesterday has a lot of like decisions to make, whereas today's topic really didn't have many decisions to make. You just kind of pump through the algorithm.
all right, I have to go. Thank you very much.
Okay, see ya.
Bye-bye.
Okay.
Okay.
Okay. Let's see. I'll stick around. So
I have 3 questions, so maybe someone who doesn't have as many wants to go first.
oh yeah. So some people like to just stay to see what other people are asking. But if so, I see. Is that what you're doing, Marcus? Just hang.
I just wanted to see what was going on because I was a little bit lost with homework 3, but I'm good now. I'm gonna try to do the catch up on the rest of the homework, and if I have questions, I'll email you.
Okay, great.
Right, bye.
And, Arafat, do you have a question, or are you just hanging to see what? Huh? Are you just hanging to see what questions?
Oh, yeah. Can you hear me?
Yes.
Yes. So on the homeworks, I saw that some you put for the math major and some are for the high school teachers.
Math majors do both.
Oh, okay. I just want to make sure.
Yeah, math majors do both. That other thing's called supplemental math majors. So that's in addition to the
Okay.
regular.
Okay.
Okay.
Okay. No. So first of all, I just want to tell you, you're absolutely right. Getting into Google Classroom, it's so much clearer what's going on. I think so many of my emails came from Blackboard confusion. I'm starting to get this. And I'm just going to say, Professor, yeah, I don't know if you saw my comment. I haven't done math in a very, very long time. So I'm just very stressful and trying to get on top of this because I struggled with I took my first math course in decades last month. So I'm just still trying to get my bearings straight. Thank God the teacher professor I worked with referred me to an algebra primer, and actually, thank God, he said to focus on quadratics. So this is starting to make it was very fortuitous because I didn't know, but a lot of this is starting to clear up for me. So thank you for Google Classroom, even though I struggled to get on it. Thank you.
Yes. So Blackboard, I'm really good at computers, right? Like, and I can't use I can't figure out Blackboard myself. I'm like baffled. So of course the students, well, for one thing, if I was better at Blackboard, maybe if I was a wizard at it, I'd be able to make it look as clear as the Google Classroom looks.
Right.
But I just abandoned it, lied to Google, told them I was not using it for a